Thank you for the introduction. So this is a joint work with Nicolas Nadisic, my PhD supervisor in the University of Mons, and Christophe Kervazo from Telecom Paris. So the starting point here is a simplex structures matrix factorization. So it's a very generic problem where given some data points, so here we call X the data points, we try to find the vertices of a convex hull of the points. So here the vertices would be the columns of W, and I will just illustrate here. If we have some data points in any finite number of dimension, so this would be the data points columns of M. The goal is to find some vertices such that, so the vertices columns of W, such that the data points are inside the convex hull of the vertices. And so given only, sorry, not Nx, given only the data points and a factorization rank, we want to estimate this W, so these vertices here. And of course, in real life situations, we always have noise, so the task is more complicated. And to solve this generic problem, we generally, okay, so one example of this problem of application is hyperspectral unmixing, where given some pixels that have values in several spectral bands, so usually between 100 and 200 spectral bands, we want to find the vertices W that will here correspond to the spectral signature of some materials, and the matrix H will just represent the coefficients, so the abundance of every material in every pixel. And to solve this kind of problem, it's hard in general, so we use different assumptions to have more tractable models and algorithms. So assumptions such as sparsity, for example, or volume of the convex hull. And here we'll focus on a very common assumption, which is separability. So in hyperspectral unmixing, it's equivalent to the pure pixel assumption. It means that here, for every material, for example, a road, we assume that there is at least one pixel in this image that is 100% road. Okay, look, for example, here we'll have probably several pixels here that will be only road. Some pixels here will be mixed with other materials. Here for the grass, we'll probably have some pure pixels near here or here. And so if this assumption is respected, which is the case in many real life hyperspectral images, then we have a whole family of nice algorithms to solve this problem. And for the second assumption, I will talk about it later. So considering the separability assumption, this is equivalent to a near separable non-negative matrix factorization, meaning that here over W, so the vertices, we can actually express it as a subset of columns of X. It means that W is present in the columns of X, like the vertices, the materials exist in the data set, in the input data points. To solve this model, we'll focus on two greedy algorithms, VCA and SPA. They're both greedy and work in a similar way. So first of all, VCA we begin with K equals the empty set. So it means we don't have any vertex. And then we generate a random direction in the orthogonal complement of the already extracted vertices. So in the beginning, this is empty. And then we select the N tree that maximizes the absolute value of the inner product of X with that direction. So what that means very concretely is with some data points, we'll choose one direction, and we'll select the data point that maximizes the absolute value of the projection, and this will be our vertex. And then we'll generate a new direction in the orthogonal complement of this, and select a second vertex, and so forth and so on. The advantage of VCA is because of this random direction. It's not deterministic, and we can run it several times, do a kind of multi-start, and keep the best solution. So it's a pretty old method, but it works very well. The only problem is it's not probably robust to noise. So in practice, it is robust to a certain amount of noise, but theoretically, we have no real guarantee. The second method for separable NMF is SPA, so successive projections algorithms. It's very similar to VCA, but instead of a random direction, the column we select in X will be the column with the maximum L2 norm. So this algorithm is deterministic, but here it's probably robust to noise. So there has been a lot of theoretical work on SPA, and under some conditions on the noise column-wise, we can prove that the algorithm will extract the real underlying vertices. Now this model is very interesting, but is robust to noise, especially with SPA. It's probably robust to noise, but it has one problem with outliers. So if we have some data points here, that could be, we could extract here the vertices, and even if we have a little noise, that is some data points that are outside the convex hull of the vertices, we'll still be able to find the vertices. But if we have a lot of outliers or extreme points, like here or here, then with a high probability, we will have the algorithm that will select them as vertices, as n members, and so the result will be completely wrong. And so here the key of our contribution is, I mean, our key motivation is to solve this problem, and the key of our contribution is add another assumption on top of the separability assumption, is that when the pure pixel assumption holds, actually very often we'll have not only one, but several pure pixels. For example, here, we see that for the world, we don't have only one pure pixel, but several hundreds of pure pixels. For the graphs here also, and for the other materials, for almost all of them, we have not only one, but many pure pixels. And so this fact is very strong, but it's true for many hyperspectral images with enough resolution. And we will use it to improve the algorithms and to solve this issue and make the algorithms more robust to outliers. And for this, we were inspired a bit by another model called ALLS. So I don't know why, but it's algorithm to learn a latent simplex. So this is more from the machine learning community. It's a very recent paper that gave us the inspiration for this work. And so they don't use the pure pixel assumption, but they use the proximal latent point assumption. So this, in very short, we can sum it up as they are p pixels or data points or whatever close enough to each vertex. Okay. And so this is stronger than separability. It's a stronger assumption, but it's true in many cases, and it can allow for more noise. So in this paper, they proved a probabilistic robustness to noise, and we are going to use this to improve the algorithms VCA and SPA. And so along with this model, they introduced an algorithm, so the algorithm ALLS, which is pretty similar to VCA, but instead of selecting one data point that maximizes the absolute value of the projection, they take the average of p data points, maximizing the absolute value of the inner product. So this step is the big difference with VCA. Instead of taking one data point that maximizes this value, we take the average of the p data points that maximizes this value. And with this algorithms comes probabilistic robustness to noise. And which is interesting, it's that this robustness depends on the spectral norm of n and not on column-wise noise like SPA. And conceptually, this is equivalent to applying VCA on the smooth data sets of the n choose p points that are the averages of all possible combinations of p data points of x. So this is why our project is called smooth separable NMF. Obviously, we don't really use this smooth data set. It's just conceptual. We don't generate the actual n choose p points. And now this paper had this very good idea, but had some issues in our opinion. That, for example, they use the absolute value for selecting the vertices. So if we have some data points here, and here, let's say these are two vertices, and we are trying to identify the vertices. So if the direction we generate is somewhere in the middle here, if we take the absolute value, the p points that maximize the absolute value, we may select some points, like if we have p equals 5, let's say, select some points from this side and also some points from this side. And so the vertex that we will extract will be somewhere here, which is very wrong. And the second problem is that they use the mean to aggregate the p points. So if we have here some data points, and here, so let's say this is a vertex, And then we have a few close by pixels and some outliers. With p equal 5, by using the mean, we'll select these points, and the mean will be somewhere here, which is also not great and not robust to outliers. So our contribution here is to take the best of both worlds, like the best from VCA and SPA, from separable and NMF on the one hand, and the best from ALS on the other hand. And this way we came up with a smooth VCA. So it's very similar to ALLS, but instead of selecting the P entries that maximize the absolute value, we take either the one that maximize or the one that minimize. So this sentence is very complicated. Don't read it. But what it means is in this situation, for example, so if in blue will be SVCA, so powers, we will take the P points here, so the one that maximize in one direction and the one that maximize in the other one. We will take the average of both, and we will keep the best average. So we'll have either this one or this one, but we'll never have some strange point here in the middle. And the second point is instead of the mean, we use the median to aggregate points. So this is quite intuitive, that the median is more robust to outliers. Here, for example, if we have these 5 points, the median would probably be somewhere here, so way closer to the true vertex. And which is interesting here, so I will not detail, but because of the way we built this algorithm, the robustness results of ALLS apply to SVCA and also to VCA, the original one that we did not have robustness results for, because VCA is SVCA with P equals 1. So if we say we only have one proximal point, it's the same as saying we have one pure pixel. And do I want to do something? No, I already did it. And in the same way, so we adapted SPA into smoothed SPA. The only difference is that we replaced the random direction in SVCA by the column that maximizes the L2 norm of the residual. And so here we don't know yet robustness results, except of course for P equals 1, which is the SPA we know. Okay, so now some experiments. So I have the preprint here. So first, I will show some synthetic experiments. So what we did here is generate W and H. Compute X equal WH and add noise. And we generated the H with different parameters that control the number of proximal latent points to each vertex. And so the metric we use here to assess the quality of the solution is the mean removed spectral angle, which is basically the kind of an angle distance between the generated W and the estimated W with our methods. So in this first experiment, so we see here when the noise is going up. Several methods with different p. So here is the parameters p. The first thing we see is that ALLS is good for small noise, but as soon as the noise is a bit higher, then our methods SVCA and SSPA are better. And also one interesting thing is that when P is overestimated, so here 50 for ALLS, the result of ALLS is actually worse than the basic separable algorithms that do not leverage the fact that there are several pure pixels. So this means that the choice of P is critical in ALLS. And we also see that it's important for SVCA and SPA, because here if P is too high for small noise, it can be a little worse than a smaller P. But still, it's not as critical. So here, because ALLS and SVCA have some random parts, we wanted to show the difference between ones, because the projection is random. So what we see here is that the best ALLS is actually better than the best SVCA, but in general ALLS is worse, and the worst ALLS is way worse than the others. And also we see that SSPA, that is deterministic, so there is no random at all here. It's almost as good as the best SVCA. And so we see that there is less differences between the median SVCA and the worst SVCA than with ALS. So here is to illustrate the importance of the choice of P. So P is the number of proximal points. So we see, so here, this is equivalent to just a separable NMF, so P equals 1. We see that for P equals 50, the result is improved by a lot. So these two here, the result is improved by a lot. But when P is too high, so here 100, 200, it's overestimated, then the result is very bad and can be even worse. So this is because if we do the average on too much points, then we begin to aggregate points that are very far away from the vertices, and the result makes no sense. So this is just to emphasize that the choice of P is important. And here was a small experiment to show if we use the mean or the median to aggregate points. So we see that the median is a bit more stable, but the mean here can have some better results. This is also because this is a synthetic data with Gaussian noise, so the mean makes sense. In real life data, we don't really observe this. And we show this nice reverse bell-shaped curve that when the parameter P goes, then we see we have some optimal here, probably near the real P. And when P becomes overestimated, then the result worsens again. And okay, this I will pass. And now on real life data sets, so in hyperspectral images, I will maybe not go into the details, but what is important to say that our methods are better than ALLS on the real life hyperspectral images, and SVCA is more stable than SSPA. And maybe we can see some images. So here, for example, in the it's the hyperspectral image urban. We see the difference between VCA, so just separable NMF with p equal 1. We see a huge gain when we consider a higher P, and it's even better for SSPA. So here there were some materials we completely failed to identify. So here, for example, we have, if I'm not mistaken, I think this is trees and this is grass, and without the P higher than 1, they are kind of mixed. And the dirt here, we completely failed to identify it. It's mixed here with the grass, and so that's it. I think I'm already too long. So just as ideas for the future, we would like to develop a strategy to find the best P automatically, because we saw the output is quite sensible to the tuning of P. Also, it could be nice to have a different P for every N member, for every material, because in some cases we could have like 100 pure pixels for one material, but 2000 for another one. And also try other aggregation methods. So for the moment, we only worked with the mean and above all the median. But we could do some more interesting schemes to aggregate the points, like maybe a manifold aggregation, or I even had some suggestion to introduce something to learn the good metric to aggregate points. So this is still open problems. And thank you for listening. And if you have any questions, I will be happy to answer. So the code is online, the paper, the preprint is online, and feel free to contact me if you have any questions now or later.
Okay, thank you very much. Are there any questions from the audience? Maybe I can start with one question. Among the different algorithms that you have shown, is there a difference in the speed of the calculation?
No. So the speed is the same, really. The complexity of the algorithms is the same, and computationally it's virtually the same.
Okay. And another question, that maybe this is naive, maybe I didn't understand very well. When you compute those vertices, how do you select the first one? Isn't that a problem?
Well, for the first one, we take as a reference the origin.
Okay.
Yeah, I forgot to tell that. And then we project on the convex hull of the origin plus the first vertex, and then the convex hull of the origin plus the two first vertices.
And the origin, does it correspond somehow to the center of all the points, or?
No, not really. Actually, not at all, because in my case, I work with non-negative points.
Yes.
So they are always on the non-negative orthant.
Okay. I see that Laurent also has a question.
Yes, thank you for your presentation, Nicolas. My question is just a detail on the slide 19. I just wanted to understand.
19?
Yes. Oh, no, it was not 19. Maybe 9 then. No, stop there. It was when you define the different. Okay, so the next one. Okay. No, sorry, the previous one. Yes, okay. So here the assumption is that there exists R index sets, okay, and then you wrote that there are P pixels close enough to each vertex. So it's really that it's not the concept of a covering here. You really want to have that each of these P pixels is close enough to all the others. It's not the fact that you'd like to have for each pixel at least one of the P pixels you have selected that is close enough.
No, it's more that for every vertex. So like if we draw here the vertices and some data points, it means that every vertex has a P closed data points.
Okay.
Like for every vertex, we have at least P data points that are close enough. Okay. For every n member, we have at least P pixels that are almost purely this material.
Okay. It's kind of okay. It's not at all a covering. It's rather a kind of density argument. So
yeah.
Okay, I see. Okay.
So it's really kind of generalizing the pure pixel, saying that okay, when we have one pure pixel, we actually have a P.
I see. Interesting. Okay. Thank you. That's it.
Are there any other questions from the audience?
Can I have a question?
Yeah, sure.
So I guess this proximal latent points assumption is to make sure that if you compute the mean, that you kind of robustly and in a stable way that you find the vertex, right? So my question is, so do you have some ideas for a heuristic method, maybe how to find out what this P should be? Like is there some, I don't know, some heuristic idea that could work? I don't know, like looking at the histograms or distributions of the points that you have, or?
Yeah, probably. So we don't know yet. It's an idea that we would like to develop, but we didn't really try yet. I don't know. One way could be to solve this with a classical method, and then look at the results and maybe the H produced with this could be a good guess for P. I don't know. Yeah, I mean it's an open question. We don't really have worked on it yet, but probably we could try and tune, because so we see in the experiments we see that when P varies, we see this kind of curve. So maybe we could, like, at each iteration, change a bit P and see if we are going like this way or this way. We could tune it a bit. It's not very clear, but I think I'm sure we can do something nice.
Okay. Thank you.
Are there any other questions? So let us thank Nicolas again and all the speakers of today. Thank you very much.